Hello students, we were discussing the synchronization in direct sequence per spectrum receiver, and in the last few modules we have in detail we have discussed about the different code acquisition techniques in the receiver. In view of that, we also discussed that synchronization in the receiver, its per spectrum communication receiver, mainly consists of two different halves, and first half is the code acquisition and second half is the code tracking. And remember, whenever we are talking about the synchronization, this is related to the code synchronization we are talking about. Apart from the code synchronization in the receiver, there is separate carrier synchronization on the top of it, where you will find that carrier phase, carrier frequency synchronization will be required. In most of our discussion and analysis, we have assumed that receiver has no clue and no a priori information about the carrier synchronization. Hence, in the most of the cases we have we have seen the architecture, we have discussed the architecture based on the non-coherent detector architecture. We have also shown that match filter architecture can give us fast acquisition techniques, and most of the cases, if the short length sequence is utilized for the spreading, then match filter can be a very good alternative also for your code acquisition than the conventional correlator and integrating dump kind of the code acquisition circuits. So, with all that knowledge of the code acquisition, today our discussion topic is direct sequence spectrum tracking, that is the next half of the synchronization. We will quickly recap about the fundamentals of synchronization in the first two slides, and then you will slowly enter into the direct sequence spectrum tracking mechanism. As I told, the first two slides will be on the recap. We understand that synchronization is a very primary function of the spectrum communication receiver, because without synchronization, codes won't be guaranteed to be aligned with each other. Hence, the spreading process won't be perfect, won't be satisfactory, and if the spreading is not done in a proper way, then your code and then successful data recovery is not possible in the detectors. So, in the discussion of that, synchronization is a very fast important block that needs to be performed in the direct sequence receivers. And basically before spreading, we have to carry about that block, and this synchronization is basically a code synchronization. Hence, your carrier synchronization will follow the code synchronization. In most of the receivers, we do go ahead like that, but I should mention here that there are some architectures, synchronization blocks and the architectures where the code synchronization block is intelligent enough to assume or estimate or predict the carrier synchronization or aspects or the carrier phase and frequency. They can actually predict, and then they can actually, there can be a with that information code synchronization can proceed. But most of the cases we will proceed with the fact that the carrier phase and frequency information is not known to us. So, your code synchronization is performed basically by multiplying the incoming signal with a local replica of the PN code. Remember, this the local replica of the PN code is generated locally inside the receiver, and so it is not coming along with the transmitter. And once we are multiplying the incoming signal with this locally generated PN sequence code, basically this is a remodulation going on of the transmitted signal or the received signal equivalently. And we expect that the PN signal which is superimposed on the data in the transmitted signal, now actually in this process actually they that signal will be, that PN signal will be now getting fundamentally multiplied with this locally generated PN code. and hence we utilize the term remodulation of the incoming signal by the synchronized local PN code. And this process of synchronization is basically aligning the incoming code with the locally generated PN code in such a fashion that the correlation between them becomes maximum, and hence your code identification and the code location identification becomes perfect. They are perfectly aligned with each other such that the output SNR gets maximized, and then the remaining portion for the dispreading operation can go ahead easily and satisfactorily, and that such that the detector can perform, the detector can detect the message without an error. The process of synchronization we have already discussed. There are basically two steps. The first step is the PN acquisition, and second part is the PN tracking. We have seen lot of the discussion on the PN acquisition already in the last few modules, and this PN acquisition mainly based on the non-coherent detector architecture as well as the match filter based architecture. For both mainly based on the direct sequence spread spectrum communication we have done. In PN acquisition, we basically do the coarse alignment of the two PN signals, incoming as well as the locally generated, within a duration of the code chip. We try to keep the acquisition misalignment within the half of the chip duration. We try to keep it actually within the half of the chip duration. The misalignment we try to keep within half of the chip duration. But at the end of this coarse estimation, which is called also the PN acquisition, there we end up with the residual relative timing offset. The remaining timing offset that is remaining, actually we try to now correct in the PN tracking section. So, if I try to picturize it, it is something like one is the coarse acquisition, another is the fine acquisition. One is the coarse alignment, another is the fine alignment. Coarse alignment is related to PN acquisition, and fine alignment is related to PN tracking. So, you cannot enter into the tracking stage directly without performing a coarse alignment of the two chips. That is the logic, and otherwise actually tracking will be very troublesome and very complicated situation. Anyway, even if you try to club these two mechanism, you have to first align it within a gross residual offsets, and then you can actually go ahead with the fine tracking, with the fine alignment within that. And hence by default, even if you go ahead with a combined circuit design, you will be ending up with first doing the coarse alignment, then doing the fine alignment of the codes. Remember, once code acquisition is done, fine tracking acquisition may be done once, but tracking is a continuous process. We never release actually that tracking mechanism to be turned off when the communication is going on. So, code acquisition may be roughly done once at the beginning of the packet arrival, but the code tracking will be continuously going on for each and every set of the data, or every set of the series, every set of the chips that you are continuously going on receiving. So, remember, tracking is a continuous process. It is followed by the acquisition. It is a fine synchronization. It is a fine alignment between the two PN sequence codes. It is the method of correcting the residual timing offset that is left after PN acquisition, and usually the order or the range of this acquisition or the range of this offset lies between the half of the chip duration interval. And this process of maintaining these two codes in the fine synchronization is basically called PN tracking, which is a topic of our discussion today. So, this was a recap about the synchronization, the fundamental brushing up the fundamentals of synchronization, and also the understanding once again the basic difference between PN acquisition and PN tracking, their interdependency, and also to understand that what is the range of the error that we are trying to correct in between in acquisition and in tracking. Now, let us enter into the PN tracking mechanisms of direct sequence spread spectrum signals. So, we understand that the process of keeping the receiver's locally generated code sequence continuously aligned in phase with the incoming code sequence is the process, and the process name is tracking. And why is it continuously needs to be monitored? Because you cannot actually leave upon the small changes in the frequency which may happen any moment dynamically because of the change of the environment, because of the incorporation of the Doppler shifts and a lot of other issues in the communication path, and hence a continuous monitoring is required, and continuously if some error is there, immediately its correction is required to be done by changing the clock offsets into the clock circuit, so that again both of them become aligned. And why it is so important? Because in the absence of that misalignment, the data detection will be under high amount of error, which cannot be which may lead you to the drop of the packet, even because packet error rate will be so high that it won't be accepted by the MAC layer next. This tracking also spreads any interfering signals, although the proper synchronization is not necessary to accomplish it. Remember that when we do the acquisition, again we utilize the PN sequence, basically like your PN acquisition. When we do the tracking, we again utilize the same PN sequence. So, basically if some interferers are remaining after the acquisition process, we have a second chance of actually spreading that interfering signals once again in inside the tracking circuit, and then further diminish the effect of the interfering signals in the next dispersing process before entering into the dispersing process. The most promising and famous circuit for this direct sequence spread spectrum tracking is the delay lock loop. We call it the DLL circuit, and there are several techniques that implement the direct sequence spread spectrum tracking, but this is the most popular one, and it relies basically on the fact that the M sequences will give always the triangular shape after correlation. So, if it is a M sequence getting used for spreading, and it utilizes a structure utilizes the fact that the correlation of M sequence, autocorrelation of two M sequences as well as autocorrelation part of the M sequences always turns down to be a triangular shape. So, based on that triangular shape, the delay lock loop logic and the architecture is established. Let us see how. Let us first, I wish to go to the next slide first to show you the DLL architecture. The DLL architecture looks like this figure 1a, where you will see that the architecture will be basically combination of three shift register stages, stage 1, stage 2 and stage 3. Remember, the output of the stage 2 is utilized for the correlation of the incoming signal with this locally generated PN code. So, second stage is always considered to be mostly corrected in sync locally generated sequence that is directly multiplied with the incoming signal for the dispersing process, and the shift register 1 is early called the early stage, and the shift register stage 3 is called the late stage. So, this is called the early gate, this is the late gate, and the central part is the actual one, I mean mostly corrected one, I should say, having minimal error, I mean minimal phase alignment, disalignment with the incoming signal, and hence it is always getting used for the dispersing purpose. The other components that are present in the circuit is something like this. There are two XORs. Actually, one XOR is XORing the incoming signal with the early gate output, and another XOR gate, the lower one, he is XORing the incoming signal or the received signal with the late gate output. The output of both the XOR gates, the upper one and the lower path, their outputs are getting accumulated here. We call it actually basically inside the accumulator there are the correlators. This is a correlation operation going on inside it, and this is the early correlator because he is utilizing the early code, and the accumulator output of and lower one is called the late correlator because he is correlating the late gate output. And after the correlated output, early gate as well as the late gate correlated output is fed to the full adder circuit, where the values of both of them are getting basically compared as well as added, and they are basically added inside the adder, and whatever the difference the adder is creating and whatever actually the equivalent value of this early gate output and the lower gate and late gate output is getting created, based on that actually the clock output of the adder gate output is fed to the clock circuit, and the clock whether the clock needs to be delayed or needs to be start early, based on the output of this adder the decision is taken, and hence the clock is driving the code generator, either delaying the code generation process or actually speeding up the code generation process or shifting it back, actually either delay it or start it early. Like that the code generation is getting controlled, and output of this code generation is fed to the first D flip flop. And as we understand the shift register architecture, the output of the first D shift register is fed to the second one. Second one's output should fed to the third one. Like that the shift register architecture is generating the local PN code, and the clock here is not only actually feeding the code generation, the clock is also same with the shift register stages, so that everything in the whole circuit in the receiver is in the sync. So, that is all about the understanding the architecture of the whole circuit, and let us look now how this circuit is performing a tracking job. As I explained, there are 3 stages of the shift registers in the circuit. Okay. The last stage, which represents a delay of the 3 chips in the sequence, it is the late code. So, it is having 3 actually with respect to the first one, it has a delay of 3. Middle one is used to decorrelate the incoming signal, and the first sequence path, the first stage output is called the early code. So, we have 3 codes, one is the late code, second is the early code, and middle one is actually the correct code, I should say. The incoming code sequence, they are modulo 2 added to the early local PN sequence in the upper path, as we have explained in the diagram. And if they are synchronized, if both of them are synchronized, then the correlation function at the top one will be showing how. See, what I am saying is, now let us see a situation when this upper code or upper XOR, if I see the output of this upper XOR, if he is having an input from the early code and he is having a received signal. We will think a situation when this early code and the received sequence both are in sync. So, they are perfectly matching in phase. Then what will happen, that the output of this accumulator early correlator output, I will be able to see like this. I mean, this early gate will be slowly increasing over the chip interval, and then the next chip interval it will come down slowly. Okay. Similarly, if I look the lower one, this is having an input from the late gate, and this is the received sequence also. So, the output of this second correlator here, we will get a late gate output like this. Remember, if we consider that there is a gap of the chip interval is equal to 1. So, then the late gate will start 1 chip interval delayed than the early gate. So, if I compare this with respect to this, you will get actually one chip interval delay. If I consider that this guy is having 0, it is a correct synchronization point, kind of correct code state. So, let gate will be giving me the structure like this. So, what is happening at the output of the full adder? So, accumulator output 1, he is giving a diagram like this. Okay. Let gate output is giving me the output of like this. Okay. So, the full adder, the output of the full adder, if I try to go ahead and try to look into it. So, see, actually here the voltage is coming down and here the voltage is going up. So, the voltage will come down and then finally it will go down even, because it is further let gate is again driving it towards the down. So, you will get a point when there is a crossover happening. We call it a in sync point. Remember the point, this in sync point, this is basically a balancing point between the early gate as well as the late gate. This balancing point will indicate exactly will happen at the middle of this chip duration. If you are if you are actually when there is a perfect it should be happening at the center part of it, if the code sequences are perfectly aligned and they are having the same length and all. But what will happen that if something, if some extra jitter is also not getting added between them, and if you are not getting the in sync point here, if you are actually the output voltage of this adder, full adder circuit is somewhere such that you are either you are here or you are here. So, in that situation the adder output will never give you 0. The adder output will give you either some positive value or some negative value. If you are getting some positive or negative value, that means the phases needs to be corrected from by the clock circuit based on where you are in a early stage or you are in the left side of the sync point or you are on the right side of the sync point. The phase will be either delayed or it will be it will start early, and hence that instruction will go into the code generator by controlling the phase of the code generator or the timing, adjusting the timing point of the code generation, and that correction will be done and applied accordingly in generation of the local PN sequence. So, that is a concept that early gate and late gate with a perfect synchronization with the perfect synchronization of the received sequence, they give actually a very symmetric architecture. And if this synchronization is not there, that is why actually you will be either in the left side or right side of the balanced point, and based on that you are going to trying to adjust it such that you are coming back to the balanced point once again. Okay. So, that is about the direct sequence tracking mechanism by the architecture of the early late gate. Okay. And this is the explanation whatever we have already discussed in the last slide. There is a difference in the two correlation functions. When they are in sync, that will come to the bottom, and if they are in sync for the upper cases, it will come in the upper one. And there is a balance point which always occurs at a fixed point in time after a chip starts, and if this point occurs at some other time than the center point of a chip duration, then actually your synchronization is disturbed. You have to re-establish it either by delaying or by advancing the clock. So, that is the final idea. Remember that this architecture and this philosophy also can be generated by some different kind of the receiver architecture, and that we will discuss in the next slide. That is another example of the correlator that would work in this architecture, and this is a straightforward parallel implementation of the correlator with the shift register sequence and the exclusive OR gates. How? Look at this architecture. So, This is the combination of the all XOR gates and the shift registers in the circuit, and the received sequence are getting fed and stored in the upper shift register. Reference sequence, the locally generated PN sequence, I mean, they are generated and they are stored here. So, n bit or n chip locally generated PN sequence is stored in the lower register, and incoming signal of n chip incoming signal is stored in the upper shift register. Remember, clock is synchronized between the reference sequence and the receive sequence, such that whenever the bit by bit XORing will be happening, and for each and every bit we have a dedicated XOR gate architecture, and from 1 to capital small n number of the chips we have n number of the parallel paths, and they are getting bit by bit XOR operation is going on. Output actually also you are feeding to the adder circuit. So, it is equivalent to the circuit that we have earlier discussed, and this can be equivalent, they both of them are, and if you try to see the output, you will be able to see that whenever the things are not in sync, you will be getting a adder output will not be synchronized at the sync point, and you will get some value based on that, whether the value is positive or negative. Based on that, clock pulse can be adjusted, and you can be either clock pulse can be either delayed or it can be advanced, so that you can control the generation of the locally generated PN sequence phase. Basically, you are controlling the waveform generation of your local generator, code generator, such a way that you get aligned with the code sequence within the remaining error that is left by the code acquisition mechanism by tracking.